Okay, welcome back. So now, as usual, the residual sums of squares, that is SSE, the error sums of squares, is divided by its degrees of freedom to yield an estimate of this common variance sigma squared. So the mean square residual, S squared y given x, is the sum of the square deviations of each observation about the predicted value divided by n minus 3. And again, it follows the general rule that it's the number of observations that I started with minus the estimated number of regression coefficients. Now, there are two basic inferential questions that are associated with second-order polynomial regression. The first question is the overall regression model significant? And the second question is, does the second-order model explain significantly more than we were able to achieve with the straight line model? Because if it does, then we're going to go with the more complex model. So first, let's talk about the test for the overall regression. So the null hypothesis here is that there's no significant overall regression using both x and x squared. And the alternative is that there is a significant overall regression. And to do this, we use the F test, which is the mean squared due regression over the mean square residual. And we compare this to the F distribution with 2 and n minus 1 minus k degrees of freedom. Well, we saw this in the computer output. Here, we saw that this F test was 35.37, and it was the mean square for the model divided by the mean square for residual. And so here it is, F is 35.37, and comparing that to the F distribution with 2 and 26 degrees of freedom, even the 99.9th percentile of that distribution, the critical value is 9.12. So therefore, we reject the null hypothesis. The p-value is less than 0.001. Now, this F test is not equivalent to any t-test. And the reason is that here, what's true is that when you have an F with 1 and something degrees of freedom, there is a corresponding t-distribution. But an F with 2 and something degrees of freedom, there is no corresponding t-distribution. And then we can compute the multiple r squared. R squared is the squared multiple correlation coefficient, which is the proportionate reduction in the error sums of squares obtained by using x and x squared instead of the naive predictor y bar. So in our case, r squared is the due regression sums of squares over the total sums of squares. Our example, r squared was 0.731. 73.1% of the variability in blood pressure is explained by both age and age squared. And this F test also allows us to test the hypothesis that r squared is equal to 0 versus the alternative that r squared is greater than 0. R squared is the population correlation coefficient. So in fact, we would reject that as well. We think that r squared is not equal to 0. We've explained significantly more of the variability in y through the use of both x and x squared. So as was true for the straight line model, this model is statistically significant. Now, the second important inferential question in a polynomial regression setting has to do with a test for the addition of x squared to a model that already contained x. So the null hypothesis is that the addition of the x squared term to the model does not significantly improve the prediction of y over and above what we were able to achieve by the straight line model. And the alternative is it does add to the prediction of y. Now remember, r squared, notice my notation here, little r squared, that's the proportion of the variability in y explained by x for the straight line model, and it was, for the straight line model it was 71.2%. R squared for the second order model is 73.1%, so I've explained an additional 1.9 percentage points. But more variation will always be explained by adding terms to a model. So it's not surprising that went up. The question is, did it go up enough to warrant including that variable in the model? So the question here is whether the increase, that is 73.1% minus 71.2%, that is 1.9 percentage points, represents a significant increase in the variation explained by the additional term. That is 1.9 percentage points enough of an increase to warrant adding the x squared term to the model? And to answer this, we compute the extra sums of squares due to the addition of x squared. And this appears in the analysis of variance table under the source heading regression x squared given x. And the way you compute the extra sums of squares, as we talked about, you take the due regression sums of squares of the full second order model, and you subtract the due regression sums of squares of the first order model. So in our example, the due regression sums of squares for the straight line model was 6110.10. The due regression sums of squares for the second order model was 6273.40. So the extra sums of squares is the difference between 6273.4 and 6110.10, or 163.30. And to test the hypothesis, we compute the F statistic, which is going to be the extra sums of squares due to the addition of x squared to a model that already contained x. The extra sum of squares divided by 1. 1 is the difference in the number of variables in the two models you're comparing. So you're comparing a model with x and x squared as opposed to a model with x. So there's one variable difference. So that's 1 degree of freedom. And in the denominator, you have the mean square residual for the full second order model. For the full model, the model contains both x1 and x2. That's the mean square that we use for this partial F test. And this is compared again to the F distribution with 1 and n minus 1 minus k degrees of freedom. So in our example, we have that the extra sums of squares divided by 1 is 163.3. The mean square for the model, the mean square for the model that contains, the mean square residual for the model that contains both x and x squared is 88.69. And so comparing this to the F distribution with 1 and 26 degrees of freedom, we find the p-value is between 0.10 and 0.25, not significant if you're using a 0.05 level. Even if you're using a 0.10 level, it's not significant. Another way to perform this test is to compute the t, and where you take the estimated coefficient over the estimated standard error, and you compare this to a t distribution with n minus 1 minus k degrees of freedom. So again, what you got to see is that this t-test for h squared, for example, the t-test here, 1.357, with p-value 0.186, is exactly equivalent to the partial F test comparing two models. The model that adds, the model with h squared and h is compared to the model with just h. Okay? And so if you could go ahead and compute the partial F test, or you can simply take this t, and this answers the question, is the addition of h squared to a model that already contained h significant? And the answer is no. Remember I said that the p-value is somewhere between 10% and 20%. In fact, it's 18.6%. That's the partial F test. Now this partial F test here, this asks the question, is the addition of the variable age significant to the model that already contained h squared? In my way of thinking, it's kind of a dumb question, because you wouldn't really fit a model with just h squared in it. Okay, so even if you found that it was highly significant, it wouldn't matter, because you wouldn't really fit a model just with h squared. You'd fit a model, if you're going to put an h squared term in, you'd also want an h term in. So you want h and h squared in the model. To put a model just with h squared in by itself is essentially fitting the full model, beta naught plus beta 1x plus beta 2x squared, where you force beta 1 to equal 0. So, you know, you can do it, but not usually done. So, so that's the, so that's the way this t-test that we see from the table. These are in fact partial F tests, and they're partial F tests, and they're done just the way we said. You look at the difference between the sums of squares for the full second order model and the straight line model. You get the difference in sums of squares divided by 1, divided by the mean square residual of this full second order model. And that is what we call the partial F test. That's asking the question, is the addition of x squared to a model already contained x significant? This t-test is exactly the same thing. T, which is beta hat 2 over the standard error beta hat 2, is asking the question, is beta hat 2 significant if you already had a model that had beta hat 1? So is the putting in of the new term statistically significant? So this is these are, in fact, the partial F tests. And so what do we conclude? Do we need h squared in the model? Well, we would conclude that we don't need h squared in the model because it's not significant. It does not make a significant contribution. So this additional 1.9 percentage points that we got from r squared isn't really enough to say that we should go ahead and fit the more complex model. Okay? All right, let's have a break, and then we'll take one more example of polynomial regression just to reinforce these ideas.